We are back for more optimization. So, how many of you drink soda pop? Or beer? Or what else comes in a 12-ounce can? Did you ever wonder why those cans are shaped the way they are? Did they ask a mathematician how to shape a 12-ounce can to put pop or beer in? I don't think they did, because if they did, they would have designed the cans a little bit differently. Let's look at what I'm talking about. I want to design a can to hold 12 ounces of liquid. And I want to design the can so that I use as little aluminum, isn't that what they make cans out of now? Design a can that uses as little aluminum as possible to hold the 12 ounces. So if you think about it, you can have a can that's really long and skinny, right? Right? Or you could have a can that's really low and wide. And this could hold 12 ounces, and this could hold 12 ounces also, but neither of those is probably, I think both of those are going to use a lot of aluminum. So what would the can that uses the least amount of material to build it, that still holds 12 ounces, what would the dimensions of that can be? So that's the problem that I want to look at here when we're talking about applied optimization. So we want a can to hold 12 ounces of liquid, and we want to find the dimensions of the can that minimize the amount of material that we need. And so another way to talk about this is to say that I want to minimize the surface area, right? So I'm talking about the aluminum that goes around the outside of the can, and then also the bottom of the can and the top of the can. So that's the surface area, okay? So we're talking about a cylinder, right? And a cylinder is determined entirely by its radius and its height, okay? So the top and the bottom, of the can are circles, and so the area of each of the circles is pi r squared. So pi r squared each, so we'll need two of those, right? And then what about the area of the outside part of the can? Well, if you cut the can open and lay it out, if you take the top and the bottom off of it and then you cut this open like this and lay it out, you'll get a rectangle, right? And the height of the rectangle is the same as the height of the can. What's the width of the rectangle? It corresponds to the circumference of the can, right? And circumference is 2 pi r, okay? Plus the sides, which is 2 pi r times h, right? Okay? So sometimes when you're doing these applied optimization problems, you need to pull out a couple of tricks from geometry, and you'll always be able to look those up. You can look them up on the internet. You can check with the people in your group. You can ask me. We're not going to leave you hanging there, okay? All right, so we want to minimize two pi r squareds plus 2 pi r h. This is the top and the bottom of the can, and this is the material that it takes for this side walls. So one of the things that you have to think about when you're doing these optimization problems, if you tell me that you want me to minimize this, well, I'll just make everything equal to 0. That'll be pretty minimal, right? If you don't do anything and you don't build any can and it doesn't have any cost to make it, that's minimized, right? So what's keeping me from doing that? The fact that I want it to hold 12 ounces, okay? So this problem is easier to do in metric, so I'm just going to change that real quick. So this is 355 milliliters. centimeters. Okay? All right. So a milliliter is a cubic centimeter, and that's why it's so easy to work with these. So that's the volume of the can, right? What's the volume of a cylinder? Should we Google it? So here's the function that we want to minimize. I will call it A for area. And here's an equation that keeps us from just making R and H both equal to 0 and walking away. So in the previous lesson, we talked about how to optimize a function, but we need for the function to be a function of one variable, right? And so this function has R's and H's in it. And this is an equation that gives us a relationship between R and H. So just like we did at the beginning of the last lesson, we're going to solve this equation for one or the other of the variables and then substitute what we get back into this thing to get rid of, well, this H. Okay? So if pi r squared H is equal to 355, then H is equal to 355 divided by pi r squared. And now we can take this and put it in here. And then we can write A all in terms of R. Okay? Okay, so H is gone and we have everything all in terms of R. What are we doing? We're trying to minimize this thing. So this is calculus. So we're going to take the derivative of this thing and set it equal to 0 and look for the bottom parts of the curve, right? So before I take the derivative, I want to clean this up if I can. And I can cancel this pi. I can cancel that R with one of those R's. And so I'll write this like this. Okay, because 2 times 355 is 710, and this R that we have still in the denominator, I moved it up to the top and put a power of -1 on it because I'm just going to use the power rule to find the derivative. Oh, the sun's going away. I'm going to turn the light on. Okay, so this is the function A, and we want to take its derivative with respect to R. So that's what we'll do. So here's what we get, and I've set the derivative equal to 0 so that I can look for the critical points, right? And so when I solve this, let's see, what do I get? So if I move this over to the right, then I get this. I'm going to multiply both sides by R squared. How do I know that this value of R represents a minimum and not a maximum? Here's A right here, so I could graph A and check to see that this really is at the bottom of one of these curves. Here we have the function, and the window looks like this because the thing gets pretty big, and if you graph it, there you see it, and 1, 2, 3, 4, so our value's right about here, and it does appear indeed to be a minimum. Okay, so all right, so that's what R has to be. Great. We want to know the dimensions of the can that minimize the amount of material used, so that means we need to give R and we need to give H. So where's the relationship between the two? Here they are. Here it is. So in order to get H, I just take this thing and do this to it. So 355 divided by pi times that thing squared. What do you notice about R and H? Do you notice something weird about R and H? H is exactly 2 times R. So the radius is half of the diameter, right? So that's what the can would look like in inches. In centimeters, it would look more like this. So the shape of the can is as close to like a cube, a perfect cube, as we can get it. Why do you think that they didn't make cans like this? I mean, it uses less material to build the can. Why don't they make cans in a shape more like this? Probably because, you know, like my giant drinking cup here, they're really hard to hold on to. I think we made cans to have the more elongated kind of shape that they have because it's easier for a normal person's hand to hold on to it. Slug that pop or beer or whatever it is. Okay, so that's an example of an optimization problem. It's pretty crazy, huh? Let's look at what we did here and try to come up with a list of here's what you do to solve one of these. So what did we do here? We decided on the function that we were going to optimize, and to do that we had to look a few things up, right? And then we also wrote down the constraint. That's the next thing that we did. And then we did this thing where the arrow is. We solved the constraint for one or the other of the variables and plugged that into the function that we're optimizing. That's the next thing we did. Then we cleaned that up. Then we took the derivative. And then we set it equal to 0, and we solved it. Then we checked to make sure that the solution that we ended up with really did give us a max or a minimum. And then what we didn't do was answer the question. And so I think I'm going to type all of this up and insert it now. Let's take another look at the fence against the building, or the pen that we're building against the building. What if this time, instead of just having 3 sides of the pen be enclosed with fencing material, what if we said this part and this part are going to be made a fence, but the edge of the pen that runs parallel to the building is going to be made of shrubbery? What if? And what if the fencing costs $20 a foot, and the shrubbery to have it put in costs $50 a foot? How big should the pen be to maximize its area? So I'm still going to call this X, and I'm still going to call this Y. I want to maximize and then what's my constraint? My constraint is that I'm not a millionaire. My constraint is that for this project, I have $1,000 to spend. So $20 a foot. So this side costs $50 a foot. These sides cost $20 a foot, and I have a total of $1,000. So my constraint is that I can't spend more than the money that I have, okay? So if X is the number of feet that's going to be replaced with fencing material, and Y is the number of feet that's going to be replaced with shrubbery, then my total cost is the cost of X times X plus the I'll write it down. Right, because $20 a foot times the number of feet here and here. So if I take out the dollar signs and clean this up, I get this, okay? So that's great. And now what is the third thing that we do? Oh yeah, we take the constraint equation and we solve it for one or the other of the variables and then plug back into here. And we like working with X, right? So let's solve the equation for Y. Looks like this, right? And then what do? We take this. And we plug it in here. And I think that's step number 3, right? So now our equation looks like this. And since I know I'm going to be taking the derivative of this thing, I want to clean it up a little bit. In fact, I'm going to go ahead and distribute this. 1,000 divided is 20x minus 4x squared. So we've cleaned this up. What is the next thing that we do? We've got the function, and now we want to take its derivative. So a prime is 20 minus 8/5 x. Take the derivative, and now we're going to solve the equation. Well, if I move that over to the right, I get 8/5 x is equal to 20. And if you multiply both sides by 5/8, you get x is equal to 12.5. All right. Now we need to check and see that this really does correspond to a maximum. I had to look and see, what are we doing? We're maximizing. So how can I be sure that this corresponds to a maximum? Well, you can graph it on your, you can graph this on your calculator if you want to, but I can see that it's a parabola that opens down, okay? So any critical point that I find has to correspond to the vertex. So I know this is good. So check to see that this really is a max. I just did that using my brain. And then the last part is to answer the question. And the question is, what should the dimensions of the pen be? So I've got the x part of the pen. What should the y part of the pen be? Oh, here it is. This is the equation, one of the versions of the equation that relates x and y. And when you plug in, did I do this? Yeah, when you plug in x is equal to 12.5. Did I do that right? Let me just double check. If x is equal to 12.5, then we have 1,000 minus 40 times 12.5 divided by 50 Yeah, y is 10. So the answer to the question is, and I'm not going to write it, I'm just going to say it. The answer to the question is that the side of the pen that is going to be replaced with fencing should be 12.5 feet wide, and the side of the pen that's going to be replaced with beautiful flowering shrubbery should be 10 feet long this way. Okay? How about one more? Okay, let's suppose that we have a piece of, let's say, cardboard that's 10 inches by 15 inches, like this. And we want to cut squares out of the corners of the cardboard. Throw them away, throw the corners away so we don't have them anymore. And what we'll end up with is like a big fat cross. Or you could say it's got flaps hanging off the end. So if we fold along the dotted lines, we'll get a box, right? Like a low box, like the box that your mom puts a flannel shirt in to give you for Christmas. Like a box, you know. So we get a box, and the problem is this. How big should the squares that we cut out, how big should they be to maximize the volume of the box? So how big should the squares be so that the volume of the box that we end up with is as big as it can be? All right. What's the volume of a box? The volume of a rectangular solid thing, it's just the length times the width times the height, right? So volume So how big should the squares be? Well, what if we use x to talk about the side length or the height of one of the squares, right? So they're x by x, okay? So after we fold these things up and we get this box, how tall will it be? The same as this, right? So the height of it is x. So the height is x. Well, I'll wait till I have them all. Okay, so it's x units high. How wide is it? The width goes from here to here. Now the width used to be 15 until we cut a square out of here and a square out of here. So it's 15 from here to here, but from here to here, it's 15 minus that x minus that x. So the width is 15 minus 2x. And the same kind of thinking goes for the depth of the box. It was 10, but we cut x out of here and x out of here, so it'll be 10 minus 2x. So the volume of the box is what we get when we multiply all of these things together, right? All right, so we're going to maximize that, right? Maximize this. So that's the first thing on our list. What's the constraint? Well, the constraint is that the piece of cardboard is only 10 by 15 inches. So could x be equal to 47? No. Because you don't have 47 inches to work with here, right? Could x be equal to -3? No. X is the dimension of the chunk of cardboard that you're going to cut out of the corner. So x has to be positive, right? I guess it could be equal to 0, then you don't do anything and you don't get a box and you don't get a Christmas present. And the volume would be equal to 0, so that's kind of dumb, so I'll just say x has to be positive. And then, what's on the other end? How big can it be? Well, we're restricted here by the short side of the cardboard. If I've got to get a square out of here and a square out of here, then the biggest the squares could be is 5, right? Right? So the constraint here is that x has to be between 0 and 5. So really we don't have anything to plug in because we already have the volume entirely in terms of x. So let's just clean it up and take its derivative. Right, if I multiply this part times this part, I get that. And so 4x cubed minus 50x squared plus 150x. Right, so v looks like this. And then, so I've cleaned it up. That's step number 4, I think. I wrote them down, yeah. So we didn't have to do step number 3. What's step number 5? Do you know? Take the derivative. Now, we need to solve this, and I can tell you that the chances that it will factor are very small. So let's use the calculator to find the solutions to this quadratic.
Okay, so we need positive 100. We'll do plus first. The square root of 100 squared minus 4 times 12 times 150. Close the square root, close the numerator, and we want to divide that by 2 times a, and a is 12, so divide by 24. So there's one solution, and the other one, we just need to change the plus right here to a minus. So we'll change that to minus. And there are the two solutions, 6.37 and 1.96.
Okay, so using our calculator to compute the quadratic formula, we get these two answers. So which one do we want? Well, if x has to be between 0 and 5, then we don't want the one that's 6.37, right? So we'll throw that one out. We'll keep this one. We need to make sure that this actually corresponds to a maximum. So let's grab the calculator again.
So we're graphing the function that gives us the volume, and we want to check to make sure the point where x is equal to 1.96 really does correspond to a maximum. So here is the window that I've set up, and the graph looks like this. And at the point where x is equal to 1.96, you can see it blinking up here. We really do have a maximum.
And then to answer the question, this will give a volume of, so let's just plug in what we get for the volume when we use this x. And those are some examples of applied optimization.